All right, welcome to this video. Today we'll be doing the Analysis and Approaches paper, higher level. We'll be doing a paper 2 from May 24, Timezone 1. So let's begin. All right, so number 1, we have a financial mathematics question. So you could use the present value, future value feature on your calculator with accounting. But you could also just use simple, arithmetics and geometric sequences and series. So let's dive straight in. So Darren buys a car for $35,000 and it decreases by 15% in the first year. So if you want to find the value of the car at the end of the first year, all we got to do is simply multiply 35,000 by 0.85. Okay, so if you do that on our calculator, we should get 35,000 times 0.85, which is 29,750. Right? And after the first year, the value of the car decreases by 11% in the subsequent years. So let's find the value of Darren's car 10 years after he bought it. So we could have 29,750, and then it becomes 89% of itself because we decrease it by 11%, and this happens for 9 years, right? So the first year it was 35,000. The second year, it's 29,750, and then each year after that, we multiply it by 0.89. So if you were to do that, it gives us $10,423.10. So 10,423.10. But if we were to round to the nearest dollar, it would be 10,423. Okay. So that was a pretty simple question. In your calculators, you could also do, like n equals 9, I equals negative 11%, and present value is 29,750. So basically what that does is instead of using this calculation, it automatically plugs it in, but with the appropriate years and interest rates and the starting value. Okay, so the first page is pretty much easy, but let's now move on to part C. So after n complete years, the car's value will depreciate to 10% of the original value. So if it started at $35,000, after n years, we know that it's going to be like $3,500. So you might be tempted to just do like 29,750 times 0.89 to the power of n. And we might want to say, when does that become less than 3,500, right? So that would tell us the value of n needed, so how many times this depreciation has to occur. But here's a catch. N complete years starts counting from when Darren first bought the car, right? So actually, when n equals 1, the car's value is 29,750, and then when n equals 2, it's 29,750 times 0.89, right? And when n equals 0, the value is actually 35,000, but it's like kind of detached because in the first year it depreciated by 15%. So what you do here is you would actually write 29,750 times 0.89 to the power of n minus 1 and set that less than 3,500. So that way, when n equals 2, we know that the depreciation has happened only once. And when n equals 1, the value would just be 29,750. Okay. So we just want to graph n versus the value of the car. And if n equals 1, we would expect to see 29,750. And when n equals 0, we should see 35,000. But the graph wouldn't really reach there because like in the first year, we just multiplied 35,000 by 0.85. So it's not like a continuous function. But anyways, let's just graph this, see what we get. So we get 29,750 times 0.89 to the power of x minus 1. Then we get the threshold value of 3,500. And then if you were to graph this, we can find the intersect easily. Second trace intersect. So it seems that the two are touching somewhere near like the 20 mark. So the intersection happens in 19.36 years. And so like in 19.36 years, the car's value is less than $3,500. So If you want complete years, we would want 20 years, right? Because if 19 years has passed, the car's value will be slightly above the 3,500 mark, but after 20 years, it will now be lower than the 3,500 mark. Okay. Next, let's move on to number 2. So there's a monument in the shape of a right cone, and the vertical height is 20 meters, and Oliver is standing 5 meters from the base. His eye level is 1.8 meters above the ground, and the angle of elevation, it's all pictured here, is 58 degrees. So let's find the radius of the base of the cone. So what you do first thing is just annotate all the information that you have. For these like geometry problems, especially if it's a 3D one, it gets pretty confusing. So you want to be careful of how you like label all these auxiliary lines. So we have 5 meters at the base, 1.8 meters, and we want to find the radius of the base of the cone. So we want to find this R value here, right? So what we could do is we could say this is 18.2 meters. Because the full cone is 20 meters, but we subtract 1.8 here, and this is 1.8. So we can use a few similarity relationships. Like if you say what is tangent of 58 degrees, it's going to be the opposite over adjacent. So we could get like 18.2 meters as our opposite side length, and R plus 5 as our adjacent side length. And that's how you would find R in this case. Yeah, so first things first, we could do that to find R. So R is going to be 18.2 divided by tangent 58 degrees minus 5. Make sure that you're dealing with degrees, not radians. So after you check your degree mode, we can now do 18.2 divided by tangent of 58 degrees. And then we subtract 5. So that's going to give us 6.37 meters, which is our base of the cone. Right? So part A, that's pretty easy. Let's go to part B. We now have the volume of the monument. So we want to find the cone's volume, right? So the cone's volume is going to be standard like pi over 3 pi r squared h, right? And we just want to figure out, so we know the height and we know the radius, so we just gotta like put it all together. Right? So 1 over 3 pi r squared h. So we get 1 over 3 times pi times 6.37 squared times 20. Okay. So using our calculator, we would get. Quick tip here is instead of just doing 6.37 squared, you might want to use the stored value before rounding, because premature rounding may lead to you being slightly off. Usually it doesn't matter, but just in case. And that gives us a volume of 850.54 cubic centimeters, or cubic meters. And this would round to around 851 cubic meters. Okay. So that's the volume of the monument. Now on to number 3, we have statistics. So we first have a normal distribution. It's a bell-shaped curve, symmetric about the center, the mean, and it has a mean and standard deviation. So we would first sketch out our normal curve and annotate it with like 10 and standard deviation of 2. And we want to shade in the area that we want. So if this is the distribution for x, we want the probability where this is greater than 10 by 1.5 standard deviations. So 1 standard deviation is 2. 1.5 standard deviations would be 3. So we would have 13. So shade in the area to the right of 13 and we're good to go. So finding the probability where x is greater than 13, that will require the use of norm CDF. So we have norm CDF, mean is 10, sigma is 2, the lower bound is 13, the upper bound is going to be some large number. So you have second distribution, norm CDF, and we have The lower value is 13. The upper value, we can enter a very large number, 10 and 2. And this should calculate the shaded area, which turns out to be 0.0668. Okay. So the probability becomes 0.668 or 0.668. And then let's do part B. The probability that x is k standard deviations above the mean. So in this case, we're given the probability. So the probability, or x, is greater by the mean, which was 10, by k standard deviations. So that would be 2k. That is given to be 0.1. So we want to find the value of k. So if you were to sketch the same normal distribution, we would actually have the right tail where this is 0.10. So the left area is 0.90. And this value is going to be 10 plus 2k. So the feature on the calculator we want to use would be the inverse norm. Because what the inverse norm does is it takes the area to the left of the curve, the left tail area. So you would just put in inverse norm, area is 0.90. And then you would enter the mean and the standard deviation of the curve. And then that would kind of give you the boundary value here. Okay. So if I have a normal distribution of mean 10, standard deviation 2, and if the left area is 0.9, what would my value have to be? That would be 10 plus 2k. Okay. So let's look at what the calculator gives us. Inverse norm, and we get 0.9, 10, and 2. So it should be 12.5631. That's going to be 10 plus 2k. So if you subtract 10, divide by 2, that's going to give our value of k. K is then going to be 1.28. Okay. So that's how you would solve this problem. Next, let's go to number 4. We have kinematics, and well, it's a combination of kinematics and trigonometry. So we have a trigonometric function where v is 2 times sine of 0.5t plus 0.3t minus 2. So actually it's a trigonometric function combined with a linear one. So there's no way you'd be able to easily draw this by hand or in your head. So you have to use our calculator. And the shape is given right here. Okay. So usually what we want to look out for would be like the intercepts, the max values, min values, right? Because the intercepts or the zeros would be when the direction is changing, right? Because the speed is going from positive to negative, right? And then we might look for maximum speeds or minimum speeds, or we might look for maybe inflection points because that's like max area and whatnot. But let's first enter this into our graph and then move on to the question. Okay. So we want to put in 2 times sine of 0.5t plus 0.3t minus 2. We want to graph that. Make sure that we're dealing with radians, not degrees, and we want to make sure that our windows are showing from like 0 to 10, right? So maybe like -1 to 11, just to be safe. And we are seeing from nowhere like less than -2 to 2, right? So we can just set the window slightly larger at -3 and 3. Okay, so if we graph the formula given in the problem, we get the exact same shape. So let me just reproduce this on this page here, right? So we would start off at a negative speed, negative velocity, and then we'd go up, then down, and out back again, right? So let's look for what each question is asking for. Find the smallest value of t when the particle changes direction. So we'd be looking for this part in part A, because the particle is moving in the left or negative direction, and then it starts to go right or positive. So we can just find the 0 at this point. Part B is asking for the value of t for which the displacement is increasing. So if this was distance increasing, like if the particle is going to the left and to the right and all that, right, we would ideally want only this part, because the distance is increasing, or this part because the distance is also increasing, right? And then we'd have to kind of consider, like, is the velocity in the same direction as the displacement, right? Because otherwise you'd be moving back towards the origin. But thankfully, that's only if it's asking about distance, right? In this case, it's asking about displacement. So it's simply a matter of when is our velocity greater than 0, right? So if your displacement is negative, you become less negative. If you're positive, you become more positive, as long as v is greater than 0. Okay. So for part B, we'd just be looking for this part, right? So we'd just be looking for the interval from which the particle has positive velocity. Okay. Because, yeah, like our graph cuts off at 10, so the velocity is negative here, so there's only one interval. Okay. And then C, we want to find the displacement of the particle relative to O when t is 10. So we would just use the integral of 0 to 10 of this entire graph, right, of this velocity function. And that would give us the displacement, right? If you wanted distance, you would have to put in absolute values, but here it's pretty simple. We don't have to do that. So we have that plus 0.3 t minus 2, right? So we just got to evaluate this using our calculator, and we're good to go for all 3 points here. So let's first get the 0. So left bound 0, right bound 4. So it seems that our time is around 1.69 seconds. Yeah, 1.69 seconds when the velocity is going from left to right. For part B, we want to find the other 0. 8. So the other 0 happens at 6.12 seconds. Right? So this is when t is 6.12 seconds. So the velocity is positive, and the displacement is therefore increasing when t is between 1.69 seconds and 6.12 seconds. Okay. Next, part C, we just gotta do the displacement. So we can just find the integral here. So if you do this from 0 to 10, it would just give us negative 2.13 meters. So it's just negative 2.13 meters. Simple as that. Okay. So this part is negative, this part's positive, this part's negative, but the calculator automatically does the summation for us, right, taking into account these signs. Okay, so that's number 4. Let's go to number 5. So here we have a linear regression problem. I think the concept is pretty straightforward. It's all a matter of, are you familiar using your calculator's features for this? Okay. So we're trying to find out if there's like a correlation between test A scores and test B scores, right? So basically, if we have a student who got some score like 52 on test A, would we be able to use that to predict a score for, test B, right? So the teacher finds that the regression line turns out to be this thing. So in this case, we're lucky because we usually would start this from scratch, but the answer is somewhat given, so we know if we're messing up with our calculators. So, but the thing is, we still need to enter this. It's just that we have the answer provided for us, so we can check if we made a mistake. So let's put in all the test A scores in the X here, and all the test B scores in the Y, or like list 1, list 2, and we should get the same linear regression equation, right? And then we'll be able to read off the value for R. So let's do that. We have 52, then we have 71, then we have 100, then we have 93, 81, 80, 88, 100, 70, and 61. Okay. Now going on to the L2 scores, you have 58, 80, 92, 98, 90, 82, 100, 165, and 74. Okay. So we now go to stats list or stats test or the calculate feature. So we have the linear regression feature with L1 and L2. So if you use that, we do get indeed y is 0.822x plus 18.4, and the r value is 0.901. So as long as you go to stats, lists, and then edit to put in these values, right? That's step 1. And 2, you do stats, calculate, and then linear regression. So as long as you use this feature properly, you should get the correct value of 0.901. Okay. Next, it says Giovanni was absent for test A and Paolo was absent for test B. So we can use the equation right here to predict the score for B, right? Because X is the A score and Y is the B score. So the teacher estimated that Paolo would get a 27 by using this calculation. But if you look at the data, the students whose data were taken, they're all in like the 50 to 100 range, whereas like this score is only in the 10. So some extreme event or some outlier event might have happened. So this is called extrapolation, a typical case of extrapolation. So this would be inappropriate, right? So Paolo's score of 10 is way out of range for like the 50 to 100-ish, right? Like the range of values that were used to get the linear regression line, that's way beyond the actual score here. So we can't really use this to extrapolate, because what we did is we saw a bunch of scores in this range, we drew a line, and then we're trying to predict what happens if someone gets this score right here. I mean, there's no data around this vicinity, so we can't really make that prediction. Okay. Next, in this case, we have Giovanni who scored a 90 on test B, and we're plugging that into score Y to get X. And this is also inappropriate because linear regression only predicts X from Y. Okay, so if you have Y equals AX plus B, we would say that it can be used to predict, the Y value from X, not the other way around, right? So if you know what someone got on test A and put that into this equation to get what he would score on test B, that would be fine. But in this case, we're using the Y value of 90 to predict X value. So it's not appropriate. We would have to do that again. So in order to use this appropriate method, that would give us 86. We would do the exact same thing of linear regression, AX plus B. But this time, the list 1 would go into the Y and list 2 would go into the X. Okay, so that would give us a linear regression model where the X is given by the list 1. Okay. So here, the X list is not L1, it's actually L2, and the Y list is going to be L1 instead of L2. Okay. Or we could do a second. That. So if we do that, we get Y is 0.987x minus 3.220. So here we now put in X equals 90. So we have 0.9871240.267 times 90, and then minus 3.2197058,374. And that gives us a score of around 85.6, or roughly rounding to 86. Okay. So to the nearest integer, Giovanni's score is 86. So now on to number 6. We have Happy Land, where the weather is independent of the weather on any other day. So we can just multiply probabilities. And on any day, the probability of rain is 0.2, and there are 31 days. Okay, so this is basically a binomial distribution, because if you say like X is the number of days of rain that we have in May, X could be anywhere between 0, 1, 2, all the way to 31, right? This would be a discrete distribution because we can't really have like 1.5 days, at least in this case. So we want to find out when exactly there is going to be 10 days of rain. So we could say X is a binomial distribution where there's 31 trials and the probability of success being rain is 0.2. And we could just look for the probability where X is exactly equal to 10, right? So on our calculator, we could just say this is binom PDF. There's 31 tries, the success probability is 0.2, and the number of successes is 10. So we could go to second variables, binom PDF, and then we could do 31 tries, 0.2, and then 10 successes, so that's 0.0419. Okay. So that's the probability. Without using your binom CDF, you could have done something like there's 10 out of 31 days to choose from that'll be raining. So 21 days will be not raining. And then we'd multiply 0.2 to the power of 10, 0.8 to the power of 21. Right? So that's another way you could have gotten 0.0419. And then if it rains on at least 10 days in May, we could do 1 minus probability that X is less than or equal to 10, or less than or equal to 9. Right? This is because if we're not counting for exact days, but rather like more or less days, we would use binom CDF. So the binom CDF button on our calculator, what that does is it allows us to find, so let's say we have 31, 0.2, and let's say our number is like 9. Then this would add up all the probabilities where X is 0, where X is 1, all the way until where X is going to be 9. Okay, so this is like the cumulative distribution that allows us to find like the probability that our distribution, our variable, is from 0 to this value. And unfortunately, for the older model calculators, you can't just adjust this so that we can find if X is 10 to 31, right? So oftentimes you might have to do complementary events. So that means we could do 1 minus binom CDF, right? And then we'd have 31 days, probability 0.2, and then 9 here. Okay. So if we do that right away, we would get binom CDF 31, 0.2, and 9. That would be 0.0746. Right? So if you were to have done this by hand, you would have done like 31 choose 10, 0.2 to the power of 10 times 0.8 to the power of 21. This would be the probability that exactly 10 days are raining. Then we'd have 31 choose 11 times 0.2 to the power of 11 times 0.8 to the power of 20. This would be the probability that, 20 days are not raining and 11 days are raining. And we'd have to keep on adding this until we got 31 choose 31, 0.2 to the power of 31, right? That would mean all 31 days are raining. So the algebra behind this, like doing this, algebraically or by hand, that would be brutal because there's just too many steps to enter. So the binom CDF function allows us to circumvent that process. Okay. So we get 0.0746 as a net probability there. And then the first day it rains is on the 10th day. So what we want there is we want there to be no rain on the first 9 days, right? So we want no rain on the first 9 days. And then on the 10th day, it should be raining. So we would just have 0.8 for 9 times in a row, and then we'd have 0.2. Right? So not raining for 9 times in a row, and then on the final 10th day, we would have 0.2. So that gives us a probability of 0.026. And yeah, so that would be 0.026. Or 0.0268 to 36 Okay, with that done, I think we can now move on to the next question. All right, so now let's move on to number 7. We have a differential equations problem. So we have dy over dx is x plus y, and when x is 0, y is 2. So we could try to solve this by, I guess the first default thing would be separation of variables, but if that doesn't work, we might have to consider other methods, right? We know that dy over dx would be like 2 when x equals 0 and y is 2. But I guess we have to go for the algebraic method here. So actually, we want to look at this one as this minus y is equal to x. So this is actually in the form of integrating factor, right? This is where we would use integrating factors. So if you have dy over dx plus a function of x times y is equal to a function of, say, like function of like x here. What we would do is we multiply e to the power of integral p of x, right? Because that way we'd be kind of forcing the left-hand side to enter into like a product rule of differentiation. So what that means is, in this case, p of x is simply going to be -1. So we would just multiply e to the power of integral -1 dx, or that would just be e to the power of -x. Okay. So if you multiply that, things should be easier, and we'll soon see what we mean by that. Okay. So basically, the integrating factor of e to the power of -x must be multiplied to both sides of the equation. So let's see what that gives us. Then we would have like e to the power of -x times dy over dx is equal to x times e to the power of -x plus y times e to the power of -x. Okay. Now let's move the y's to the one side here. Minus y e to the power of -x, and x e to the power of -x stays there, right? So this is a result of if this were to be u, and this were to be v prime, and y were to be v, and if this were to be like u prime. So the negative e to the power of -x, that's going to be u prime. So this is actually the result of if we had e to the power of -x times y, and if we had differentiated that, that would have given us the left-hand side here by product rule. Okay, so this is equal to x times e to the power of -x. So in order to find e to the power of -x times y, we can then integrate x times e to the power of -x dx. Okay, so the first part involved us using integrating factors, and the second part actually requires us to use integration by parts, right? Because there's a product rule, but for integration. Okay. So let's say that u is going to be x, du will be dx, dv will be e to the power of -x dx, and then v would be negative e to the power of -x. So if you do uv minus integral v du, that's going to be x, negative x e to the power of -x, and then plus integral e to the power of -x dx. Or that's going to be negative x e to the power of -x, and then minus e to the power of -x. So that's going to be the result of the integration by parts on the right. So we took a small detour, but let's come back here. So we got e to the power of -x times y is negative x e to the power of -x minus e to the power of -x here. Okay. So with that, we can now move over here to say y is now going to be like negative x, -1. And then, oh, but we also have to have a plus c here, because of the integration constant. Okay, so y is going to be negative x, negative 1 plus c times e to the power of x, right? Because if x is 0, we're able to divide away e to the power of negative x because it's a non-zero. Okay. So now comes the time to find what c would be. So if y is 2, x is 0, we would get c is going to be 2, right? So if c is, so c would actually be 3. So y would be negative x minus 1 plus 3 e to the power of x. Okay, so that's what we would get for y in terms of f of x. Okay. Okay, so now let's move on to number 8. We have a continuous random variable. So we have a probability density function whose integration should give us 1. So if you were to integrate like kx from 0 to k, add that to the integration of 2kx minus x squared from k to 2k, that should be 1. Okay, so that relationship should give us 7k cubed is going to equal 6. So let's try that. We get kx squared over 2 with definite integrals from k to 0 plus we have kx squared minus 1 over 3x cubed from k to 2k. That's going to equal 1. Okay. So if we substitute these definite integrals, we should get k cubed over 2 minus 0 plus 4k cubed minus 1 over 3, 8k cubed, and then minus k cubed plus 1 over 3 k cubed, that's going to be 1. So if you organize everything together, we should get 7k cubed is equal to 6. So let's try that. If you were to add everything up, we would get, this would be like 9k cubed over 2, the first two. And then we would get negative 8 over 3, so negative 7 over 3 k cubed. And then negative k cubed is 1. So let's try multiplying 6 to all sides. So we would get 27k cubed minus 14k cubed minus 6k cubed is 6, or 7k cubed is equal to 6. Right. So this is indeed the equation that was suggested. So we did show this relationship for k. Okay. Next, if you're finding the median of x, let's call that median m. So if you were to integrate from 0 to m, the PDF, that should be 0.5 if m were to be the median. Okay. So because we have a piecewise function, we actually need to consider the case where m is in the first region or the second region, right? So we might ask, is m between like 0 and k? Or is m between k and 2k, right? That might be the question. So what we could do is we could first find out what would happen if k, so let's just find out the integration from the left, right? So if you integrate from 0 to k, like this, so if you were to assume that, you know, like m is somewhere in between here, this area should not be greater than 0.5, right? So if you try this, we get, so note that k is 6 over 7. So let's just find out what k would be. So from earlier, we found that k is going to be 0.950. So if k is 950 here, we could evaluate this, right, and see if this is greater than or less than 0.5. Okay. So if we integrate, and we have going from 0 to 0.950, and then 0.950x dx. So that's only 0.428, right? So what that means is the median should be on the right side of this equation, right? So this went to show that our median must be greater than k, right? So then what we could do is we can now find the integration from k to 2k, and then we have 2kx minus x squared dx. This should be 0.5 minus 0.428. Oh, so actually we don't integrate from k to 2k, we would actually integrate until the median value m. Okay. Because if we integrate from 0 to k, we have an area of 0.428, the remainder of like 0.072, that must be satisfied by the integral boundary m right here. Okay. So we can actually go to our calculator to do that, because we can put in the integration operator here. So we're integrating from 0.95 to a certain value, let's say x. And then we can just put in our expression of 2 times 0.95 times x minus x squared. So this should give us 0.072 at some point. Oh, and k would be slightly over 0.95, but not too greater than that, hopefully. Right. So if you were to find out when this is equal to 0.072, we may as well just subtract 0.072 and look for the 0 there. Okay. So the 0 turns out to be 1.03, right? So yeah, the median value would have to be 1.03 using our graphic display calculator. Okay. Now let's move on to number 9. We have a typical seating problem with Alvin, Bobby, and Catalina and Daniela. So A, B, C, D, those kids are sitting as part of a group of 10 children with 10 desks. Okay, so we're trying to see how Alvin and Bobby could be seated next to each other in the same row. So let's see how that will work. So let's say we set apart like 2 seats for Alvin and Bobby. Right. So that's one method, but they could also switch around. So we could have like AB or BA. So that's like 2 seats. But we could also have it so that we have like 4 arrangements of that, right? And actually they could take 4 more arrangements on the second row. So there's actually 8 ways where we can take 2 consecutive seats that are sitting together. And then we multiply that by 2 because A and B, B and A, they can switch. Right? And then what happens is if we take 2 seats out of the equation, we now have 8 children left for 8 seats here. So there's actually 8 factorial ways in which they can be seated. So we would just do 8 times 2 times 8 factorial. And that would give us like 64 or 645,120 ways in which they could be seated. Okay, so how we do this is basically this would be the number of ways to pick out 2 seats. Then we can switch the A and B, right, or B and A. And then this would be seat the remaining 8 children. Right, so we just multiply all this together to get a total number of 645,120 ways. Okay, so find the total number of ways the children can be seated. This would be 645,120 ways, right, as we've seen earlier. So let me just copy that down here. Okay, and then for part B, C and D, right? Kids Catalina and Daniela must not sit next to each other while Alvin and Bobby are still sitting next to each other. So how would that work? We can actually take the original 645,120 ways, and we can subtract the cases where Catalina and Daniela are sitting together, right? So this is the number of ways where Alvin and Bobby are together. Right, they're sitting together, but we now subtract the number of ways where C and D are sitting together. Right, then that would give us the solution or the answer that we want, right? So let's actually draw out how this would take place. So remember that we had 10 seats here, and let's say that Alvin and Bobby take like the edge seats. Then how can C and D sit together? Well, we could say that C and D could be sitting here. Or we could say, so there's like two ways where Catalina and Daniela could be sitting. Or we could have like 4 more ways, so that's like 6 ways. So actually, Alvin and Bobby could be sitting in these 2 seats, these 2 seats, these 2 seats, or these 2 seats, right? So on the edges, that would be like 4. So there's 4 ways in which Alvin and Bobby take the edge seats. So we can say this is the case where A and B are on the edge. Right? And then C and D can take 6 seats here, and then Alvin and Bobby can change their order, and C and D could also change their order. Right? And then we would have the remaining children, right? 6 children taking 6 seats. Right? So the number of ways that Catalina and Daniela would be sitting together if Alvin and Bobby are on the edge seats would be 4 times 6 times 2 times 2 times 6 factorial. Right? And then we could also try the case where Alvin and Bobby might not take the edge seats, but rather they might take like the sample, like the center 2 seats. So if Alvin and Bobby were to take these 2 seats, then C and D, they can sit in either 1, 2, 3, 4, or 5 seats only, right? So Alvin and Bobby can take the center seats or non-edge seats. So we can say like if A and B are on the non-edges, they could take 1, 2, 3, 4. So they could take like 4 ways. And Catalina and Daniela would then be able to sit on like 5 remaining seats. And then we multiply 2 and 2 again, because A and B could be switching seats, and C and D could be switching seats. And then we have, again, like 6 children for 6 seats. So we would do 4 times, so we would do 4 times 5 times 2 times 2 times 6 factorial. So this would be the total number of cases where C and D are sitting together when A and B are also sitting together, right? So if you subtract all of this, that should give us the correct number of ways in which A and B are sitting together, but C and D are not. Okay, so it's like using complementary events to the max. So we would do 6, 4, 5, 1, 2, 0 minus brackets 4 times 6 times 2 times 2 times 6 factorial plus we'd have 4 times 5 times 2 times 2 times 6 factorial again. Right, so if you subtract that, we would get 518,400 ways, right, in which this could happen. So this kind of problem is not like a very standardized problem. You'd have to kind of count on your luck or your instincts. So if you get it, you get it on the test day, or you might be unlucky and there might be, no clear visible way for you to crack this. So what I would suggest is if you encounter such problems, don't stress too much. Like, we can always come back to this later, okay? Because you just need to see the right way to count all the different events in a way that they're, mutually exclusive, right? So that we're not double counting, right? And we also want to be collectively exhaustive. So we don't want to miss out on any of the probabilities, okay? So that's number 9 for you. Let's go to number 10. All right, so number 10, we have a trigonometric function and transformation of functions type of problem. So we would keep our calculator close by, but we also want to pay attention to details because sometimes there's like shortcuts where we don't necessarily have to punch this into the calculator, okay? So the height of water in Sulskeri, right, some like islands, is modeled by this function right here. And it seems that it's going to be sinusoidal. So we're going to be having like some periodic waves that are rocking about. So we could graph this equation first. So, and then we'll probably find like the max points, the min points, and whatnot. So let's actually graph this and move on to the next page. So we have 1.63 times sine of 0.513, and then we have x, or t, minus 8.2, and then we have plus 2.13, okay. Okay, so we also want to show from 0 to 15 hours. Okay. And we want to make sure that we see the full wave here, so we'll just zoom out a little bit. I guess the wave will be greater than 0 at all times. Right, so this is a graph that we get. I'm just going to trace this here, or it's also provided for us. So we want to find out the length of time between the first low tide and the first high tide. Okay, so we just need to find out what this is, and we want to round this to m minutes. So if you get something like 6.5 hours, do note that this is going to be 6 hours and 30 minutes, right? So we got to convert to the proper minute notation. So let's go to our calculator and do minimum. Okay, so let's find our minimum point. So right bound is 8. So if we do that, our minimum is going to be 5.138 hours. And we get 0.5 meters. And then our maximum is going to occur at like 11.261 hours and 3.76. Okay. So if you want to find the time between that, we would just do 11.261 minus 5.138. So that's like 6.123 hours. We now want to convert that into minutes. So 0.123 we can multiply by 60. So that would be like 7.38 minutes, or m would be 7. Okay, because we have 6 hours and 7 minutes. Okay. Right, so that's part A. Let's now move on to part B. Between the two consecutive high tides, determine the length and time in hours for which the height is less than 1 meter. Okay, so I guess we start off from the max point right here, because if you look at our graph, okay, so between two consecutive high tides, we just want to know when we have the height being less than 1, right? So what we could do is we could draw a function where ht is equal to 1, and then we can look for the intersections. Right. So we first get our intersection. When the time is like 3.57. Okay. So this is when we have 3.57 hours, the height is 1, and the second intersect happens when the time is like 6.71. So we get 6.71 and 1 meters. So the length in time would be 6.71 minus 3.57. So we get like 3.14 hours. So that's how long it takes for the tide to come back up, right? So during these hours, like during this period of 3.14 hours, you see that the tide is lower, staying lower than 1 meter. Okay, next, what's the rate of change of the height when t is 13? So we're just looking for h prime 13, right? And we don't need to actually use our hands for this. We can just enter this into our calculator, because if you go to second trace, we can go to dy over dx. So at around the 13-hour mark, we can find the slope using dy over dx when x is 13. Right? So if you do that, it says the slope is going to be, the instantaneous slope is negative 0.651. And units would just be in meters per hour. Right? So we get negative 0.651, that's easy as that. Part D, we have a new island, a new sinusoidal function where we have to find like A, B, C, and D, right? So let's find all of these one at a time. So what we have here is that the first low tide occurs when t is going to be 241. Okay, so what we could do is we can now say this is 2 and 41 over 60. So we'll just change this into hours. So 41 over 60, that's going to give me 0.683. So if I were to kind of sketch out my graph, the first low tide would occur at 2.683, and the height of the water is said to be 0.40. And 902, so 2 divided by 60, that's going to be 03. So at like 903, we have the tide at its maximum point, and it's going to be like 2.74 meters. And then we have, okay, so that's all that's given. So this one is going to be half the period, because the full wave is going to look like that, right? So we have half of the period, that's 9.033 minus 2.683, right? And then we can get like our center line. So the center would be, if you do 2.74 plus 0.74, 0.4, and divide by 2, the center line is going to be like 1.57. Okay, and we know we're going up by 1.17, and then we're going down by 1.17. Okay. So that would probably allow us to find the A, B, and D. Okay, so first, when it comes to the period, we know 2 pi over B is going to be the period. So B is going to be 2 pi over the period, which is 2 times 9.033 minus 2.683. Okay. So if you do that, 2 pi divided by 2 times 9.033 minus 2.683, that's like 0.49. So B is going to be 0.495. Right? So that's what we get for part B. For A, we know that it's going to have an amplitude of 1.17. So yeah, A is going to be 1.17 right away. D is going to be the shift. So normally the sine function would fluctuate about height equals 0, but since the center line is 1.57, we can say D is 1.57. And then C would be the tricky part, because if you were to have like a normal sine function, then it would start off at the origin, and it would go like that. But it seems we kind of have a function that has a minimum at this point, so we either shifted to the left or we shifted it to the right. So what we could do here is we could actually just solve for C right away by just plugging in everything else. Yeah, so if you don't want to think about us having to shift this by a certain amount and all that, what you could do is you could just substitute in this equation for C. So what that means is if you have height of 0.4, okay, so we could say 0.4 is equal to 1.17 times sine of 0.495 t minus c. But instead of t, we now have 2.683 minus c. And then we add 1.57. Okay. So if you just solve for c right here, we're good to go. So on our calculators, you'd have 0.4 minus 1.57. Then we divide by 1.17. Right. Then what we would have is sine of 0.495 times 2.683 minus c. That's going to equal -1. So we'll take the sine inverse of that. So it's -1.57. Okay. So if I were to write down the middle step here, I get -1.57 is equal to 0.495 and 2.683 minus t. Then I can divide this by 0.495. And then I could subtract 2.683. Okay. So actually, t I would send to the other side, and then I would add 1.57 and 3.17 here. So actually, if I were to write this down, it would be 2.683 minus t is going to equal -3.173. Okay. So t would just be 3.173 plus 2.683. Whoops. So this one plus 2.683. So that's going to be 5.856 or around 5.86, right? So that's going to be C. Yeah, so we're done finding C as well. C is 5.86. So we just found all the four alphabets A, B, C, and D to the three significant figures. Right, so now let's move on to part E. So we're trying to find when time is capital T, when the two heights are going to be the same. So we just need to set up the equation where capital HT, which stands for the height function of the first island, right, is equal to small ht, right, which is the height function of the second island. So we have small ht right here. So we don't need to think too much about this. We can just solve this using our calculator. So if we were to plot the two graphs, right, so let me just plot y is 1.17 sine of 0.495. And then we get x minus c, which is 5.86. And then we can do plus 1.57, right? Yeah, so we're just looking for when these two first intersect. So it's going to be like from 0 to 6, and we get 4.164. Okay, so the value of t is going to be around 4.164. Okay, so if you were to sketch here and here, these two graphs would intersect at 4.164. So t is going to be 4.164, right? Because the height at these points are going to be 0.699 meters. Okay. So we can just leave that in hours, or we could just write 4.16 hours. Okay. And there you have it. That's number 10 for you. All right, so on to number 11. We have dy over dx. So we're given the rate of change. Right. All right, so let's now move on to number 11, where we're solving differential equations. And we have the original form function, right? E to the power of x plus y is x squared plus y squared. So this is defined implicitly. And then we have dy over dx. So hopefully this will be a starting point for us to solve this differential equation like analytically or with Euler's method. But first, let's go from here to here, right? What part A is asking is to simply show that dy over dx is this expression, and we're going to use implicit differentiation. So if we have e to the power of x plus y is x squared plus y squared, and we want to differentiate this with respect to x, we're going to get e to the power of x plus y, and then x plus y prime as chain rule, and then we get 2x plus 2y times dy over dx. Right? So y squared, that's just going to be 2y according to the power rule, but then we have to multiply dy over dx, right? So this would then be x plus dy over dx, and e to the power of x plus y is equal to 2x plus 2y dy over dx. So we could rearrange this whole thing again. So we'd leave x times e to the power of x plus y on the left. We would take in 2x from the right, subtract it, and then on the left side we would send this, so we get dy over dx, and we would get negative e to the power of x plus y, and then we would keep 2y here. Okay. So if we isolate dy over dx, we would get x e to the power of, and then this would be 1, by the way, because x prime is just 1, right? So we would get dy over dx is just e to the power of x plus y minus 2x all over 2y minus e to the power of x plus y. But we could just multiply -1 to both sides, both the numerator and denominator, and we'd get 2x minus e to the power of x plus y all over 2y minus e to the power of x plus y. Okay, so in a few steps of implicit differentiation and kind of changing out the algebra here, we'll be able to show what part A wants. Okay. Next, let's show that the coordinates of P and Q will satisfy 2x squared plus ln 2x squared minus, this expression right here. So we would start off by basically solving for P and Q, right? So P and Q are actually the local minimum and maximum points. So we actually wrote dy over dx. That's going to be 2x minus e to the power of x plus y all over e to the power of x plus y minus 2y. So we basically want to set this equal to 0 to find P and Q. Okay. So if we were to do that, so what we would do there is we basically want to make sure that 2x is equal to e to the power of x plus y. And before we use a calculator, we want to solve this in exact form, right? So we could try taking the ln of both sides. So ln 2x is going to be ln of e to the power of x plus y, or just x plus y. And y would be ln of 2x minus x. Okay. So if you want to solve for the coordinates of P and Q, what we would do here is we could then substitute this into our expressions for P and Q. Okay. So So if you take our original graph here, we have e to the power of x plus y is x squared plus y squared. So for P and Q, this expression has to hold because only then will dy over dx be equal to 0. So if we change out the expression for y, we would get this expression right here. So we have x plus ln of 2x minus x equals x squared plus ln squared 2x minus 2x times ln 2x, and then we get plus x squared, right? Or, yeah, so plus x squared. So we substitute this into the original formula, and what we end up getting would be something like e to the power of ln 2x, it's just 2x on the left. That equals 2x squared, and then we get plus ln 2x squared. Right, I'm just going to write this squared on the outside, minus 2x ln 2x. Right. And then if I just move this 2x to the other side, I basically get this equation right here. So that's it for part B1. Next, I want to show the coordinates of P and Q. So I just got to solve for this one. So for P and Q, what I would do is I would just solve for when this full expression gives me, okay, so actually I just need to solve for this expression right here. Okay, so writing one more step, I'll just write 2x squared plus ln of 2x squared minus 2x ln 2x minus 2x equals 0. So using my calculator, I'll be able to find the solutions of x for which this is true, and that's going to be coinciding with the x coordinates of P and Q, right? So I get 2x squared plus ln of 2x squared minus 2x ln x, or ln of 2x minus 2x, right? So I want to look for the x-intercepts for this one. So I kind of want to zoom in on the x, so maybe I'll do from 0 to 5 maybe. And then I want to see the negatives. Yep, so if I go to second trace 0, I would get 0.331. So 0.331, and I would just put this x value into this original equation here. So ln of 2x minus x, right? But before that, let me also find the other 0. So the other 0 would be 1.84. So I believe that's going to be P, that's going to be Q, because P is on the left side. And in order to find the y coordinates, I would just put in ln of 2x. So ln of 2 times 0.331 minus 0.331. So that's negative 0.743. And for Q, I'm just going to put in like ln of 2 times 1.84 again. So 2 times ln of 1.84, and then minus x, right? So 1.84. So if we were to do that, we would get negative 0.537, or yeah, so that would be negative 0.537 for coordinate q. But actually, when we're doing this for coordinate q, we just want to make sure the rounding is there. So we have actually 1.84273. So if you actually write down all the digits, right, without the premature rounding, we would actually get 0.538. So that's why it's important to not round prematurely, but rather store your values on your calculator. Okay. So these are the two coordinates for P and Q. Let's move on to the next one. We have part C. So using the line of symmetry, write down the coordinates on the curve where the tangent is vertical. So basically what we have is, if you look here, P and Q, they can be reflected about y equals x. So when the slope is vertical, undefined. So when the instantaneous rate of change is like steeply infinite, that's the reflected images of P and Q. So all we gotta do for the next part is simply swap the coordinates. So we would get so we would get negative 0.743 and 0.331 for the reflection of P. And for Q, we'll say, we'll call it Q prime. We would just have negative 0.558 and then 1.84, right? Or, 538. And we would get 1.84. So on the graph, what that would mean is, we have our y equals x right here. And we have this graph. So if you had P and Q somewhere around here and here, we would actually have our P and Q. So our P and Q would be somewhere around here and here. So we just need to switch our x and y coordinates. Okay. Next, part D. Right. And let me just add one more drawing. So here the dy over dx is going to be 0. But here, at these points, we would see that the dy over dx is going to be undefined. Next, find the coordinates of the point on curve C where the tangent has a gradient of -1. So we want to look for dy over dx is -1. So from earlier, we said this expression was 2x e to the power of x plus y, e to the power of x plus y, minus 2y. So we want to set this equal to -1, and we would just solve for this, right? So if we would do that, we would actually get 2x minus e to the power of x plus y is equal to 2y minus e to the power of x plus y. So actually, we can kind of get ahead of ourselves and say that, okay, y is going to equal x in this case, right? But you could also just do it on your calculator. So if you do that, we would get 2x minus e to the power of x plus y. Oh, actually, yeah, the only way we would be able to do this is with y equals x, because on your calculator, you'd need an explicit equation of y in terms of x. So yeah, y is going to equal x. So we would go back to our original formula. The original formula was e to the power of x plus y is equal to x squared plus y squared. But now we're going to say, since x is going to equal y, we can just write e to the power of 2x is 2x squared. So if we were to solve for this, we'd have e to the power of 2x minus 2x squared. And then if we were to solve for this, let's see what we get. We would get negative 0.451. So x is negative 0.451. Since y is equal to that as well, we get negative 0.451. So the coordinates of the point on the curve C, right, would have negative 0.451 and negative 0.451. Okay, so we just solve for dy over dx is -1. All All right, so now we're on to our final question, number 12. We have vectors. So using the definitions of u dot product v and u cross product v, let's show this relationship. So u dot v is actually going to be u modulus times v modulus times cosine theta, right? That's what u dot v stands for. And u cross product v is going to be the same, but with sine theta, right? So on the left-hand side, we can expand this as u modulus squared, v modulus squared, cosine squared theta, plus u modulus squared, v modulus squared, sine theta, or sine squared theta. And then using sine squared plus cosine squared, that's a trig identity, right? So remember that sine squared theta plus cosine squared theta is going to equal 1. This would just simplify to u squared v squared, which is actually just equal to the right-hand side of this expression. Okay. Next, we have part B. So what we're trying to do here is we have triangle ABC, and we have vector u that's going to be going from A to B, and vector v going from A to C. So this is v, this is u. So given that u dot v is 3 and the area of the triangle is root 6, so if this triangle is root 6, what's the value of u cross v, magnitude of that? Well, naturally that's just going to be 6, right? Because if you have two vectors like u and v, then u cross product v, the magnitude of that, gives the area of this parallelogram. Half of that is going to be the triangle, right? So what we would just say is like 1/2 u cross v is going to be the area of the triangle, which is 3, or I meant root 6. So what the u cross v modulus is going to be, it's just going to be 2 root 6. Okay. So yeah, so that's how we would do part BI. BII, we would have, so we want to find the value of magnitude of u. So let's put it this way. So we have this triangle where, okay, so actually we can just find what u is going to be. So u is going to be b minus a. So what we would find is it's just going to be p q minus 1 and 3 minus 2, which is just 1. And then v, the vector for v is going to be c minus a, which is 3, 1, and negative 1. Okay. So we have that information for now. And what we could say is if u dot v is so if we have u dot v, so actually we can now use the equation from earlier. So recall that, so actually we're going to use this in part 3, so no need to worry about that right now. So for part 2, recall that from part A, we said that u dot v squared plus u cross v squared is equal to the magnitude of that, right? So let me write that again. So recall from earlier that u dot v squared plus u cross v squared was equal to u squared and v squared, right? So what happens here is u dot v is given as 3. So we can say this is 9 plus the value of this is 2 root 6. So we get 2 root 6 squared is going to be u squared and v squared, right? With that said, we don't know what u is because we don't know p and q, but we can find out the magnitude of v, right? So we get 9 plus 24 is equal to u magnitude squared times, this would be square root of 11, so that would just be 11, right? Because magnitude of v turns out to be root 3 squared plus 1 squared plus negative 1 squared, which is root 11. Okay, so u magnitude squared is going to be 33 over 11, which is 3. So u magnitude is going to be root 3. Right? That's what we get. Okay, next, hence or otherwise find the possible values of p and q. Okay. If you were to do that, I guess we could try using the u and v vectors we found from earlier. So if you were to do the dot product, like u dot v, we would get 3 times p plus q times 1 plus -1. Well, I'll just write -1. So that's just 3p plus q minus 2. Okay. That is going to equal 3. So we could say 3p plus q is equal to 5. That's one relationship we have. And then the next part we could try is, so that allows us to replace q with 5 minus 3p, right? Now we're going to use the fact that modulus of u is root 3. So if you have p squared, that's going to be p squared plus q minus 1 squared plus 1 squared. That's going to equal root 3. But instead of q, we have 5 minus 3p. So this is going to be 4 minus 3p instead. Okay. So we get square root p squared plus 4 minus 3p squared plus 1. That's going to equal root 3. Okay, so you can kind of pretend this u bar is kind of removed here. Okay, so we're trying to solve for the modulus of u represented by both the left and right side. They're equivalent, so we're now solving for p and p only, right? So we can just directly plug this into our calculator, and it should give us a certain value of p. Okay. So that should give, if you have like x squared plus 4 minus 3p squared, and then we have plus 1. We want to set that equal to 3, right? So let's just pretend that we square both sides. And then, so we get 2, which is 1 and 1.4. So p could be 1 or it could be 1.4. Okay, yeah. So there's two values at play. P is 1 or p is 1.4, in which q would be 2 or q would be 0.8. Right? So there's two sets of values for p and q, which are p is 1, q is 2, and p is 1.4, q is 0.8. Okay. Next, we're trying to look at a point D, which is new, and the vector w is defined as CD. So uw dot product and vw dot product, these are 0, so these are perpendicular. So if u is perpendicular to w, and if v is also perpendicular to w, like the only explanation where this would make sense is if w is the cross product of u and v. So how that would work is we basically have something like, so the shape overall would look something like this. We would have u going like that, v going like that, and then the vector w, right, is both perpendicular to v and u, right? So actually w would look something like that. So w is actually the result of finding the, so let me just delete this. So the vector w is a result of taking the cross product of u and v together. Okay. So if p is equal to 1, right, we can recall from earlier that u is p q minus 1, 1. So you'd have 1. If Q is 2, then we get 1. So U would be 1, 1, 1 if P is 1. And then we're taking the cross product with V, which was just constants, 3, 1, and -1, right? So now let's try to find the cross product here. So we get 1, 1, 1, 3, 1, -1. So you can use cross products in your own way, but it's 1 times -1 minus 1 times 1. So it's going to be -2. Then it's 1 times 3 minus 1 times -1. So that's going to be 4. And then we have 1 times 1 minus 1 times 3, which is -2. So this is going to be the direction vector of W. But it doesn't have to be -2 for -2 exactly. We could just say it's like multiplied by a certain vector, maybe lambda. Right? So now what we have to do here is the area of triangle ACD. So we have CA and CD. So we basically found that the vector of W is going to be -2 for -2 lambda. And lambda, so we want to find what lambda is going to be with a further hint, right? So let's say that W is given by vector CD. Okay, so if you were to draw this, we would get C and D, right? So that's vector W. And vector V was AC, but I guess we could say this is going to be -V, right? Because we have CA. So if you find the area of this triangle, it's going to be 5 square units. So if you take the modulus of V cross product W, that's just going to be 5. So you don't have to worry about, so technically you have to do like -V, but you don't have to worry about that because we're just going to solve for the parameter anyway. So like either way, it's going to work out in the end. So if you have V and W cross product, we get 1, 1, or 3, 1, -1. And then we would get something like W, which is, for now it's -2 lambda, 4 lambda, -2 lambda. So that's equal to 5. So performing the cross product, we get -2 plus 4, so it's 2 lambda. Then we get -6, -2, so -8 lambda. And then we get, so actually it's -2. So it's 2 lambda, and then this is going to be 2 minus, it's going to be 8 lambda. And then we're going to get 12 minus -2, so 14 lambda. So writing this up here, we would get V cross W is going to be 1, 4, 7, and let's say it's going to be like T, a new parameter. So whether you have like a negative version or not, the T would naturally flip. So yeah, it doesn't matter at the end. And then the modulus of V cross W, that's going to be square root of 1 squared plus 4 squared plus 7 squared times T. So that's just going to be 49, 16. So it's going to be like root 66T. So square root 66T is going to be 5, so T would be 5 over root 66, but actually it could be plus or minus, right? So the W is then going to be, so the vector W, if I were to write it like at the very top, it's just going to be plus minus 5 over square root 66, and then we're going to get -2 for -2 lambda. Okay. Or further simplifying, I guess we could get 10 at the top. So 10 over root 66, and then we would get 1, -2, and 1. Right? Or -1, 2, and -1. And we could just call this without the lambda here. Okay. So no lambda, no T. This would be the specific vector for W. So that's all for today. We just finished the 24 May papers for Analysis Approaches Paper 2, Time Zone 1. Thank you for watching.